Hello, everybody, and welcome to today's meeting on Molecular World Making of Modern Chemistry, given to us by Catherine Jackson from the University of Oxford. Catherine, it's a great pleasure to welcome you this afternoon. Could you please now give us your talk?
Thank you very much, Peter, for that very kind introduction. It is a real pleasure to be here today and to share some of my work with you. Most of my talk today is about my book, Molecular World, but I also want to tell you how I'm building on this book in a new teaching-led research project with chemists in Oxford's chemistry department, using history to reflect on what it means to be a chemist and on chemistry's place in our world. So I mentioned a moment ago that I started out as a PhD synthetic organic chemist in Cambridge. I worked for about 20 years in research, industry and education. Then I changed direction. Why? Why does a chemist turn to history? Well, I had two reasons. My original motivation was historical. I wanted to understand how and why the discipline of chemistry was built. But I since shifted to focus my work towards the pedagogical, to support chemistry's disciplinary sustainability in challenging times. And I'm thinking here about issues including equality, diversity, and inclusion, which I interpret broadly to encompass any typically marginalized group, including students, postdocs, and technicians. I'm also thinking about global problems of resource depletion, climate change, and environmental concern. So it may be history, but its concerns are present and future. As I learned more about chemistry's history, I understood my own chemical training in a new way. I came to appreciate why chemists value certain skills above others, and I began to see ways that history could help both individual students and the discipline as a whole. In a time of unprecedented challenges, history offers powerful tools in leveling the path to research and tackling global problems. Using history to enhance training in chemistry is the mission that now drives my research, and it underpins my teaching in Oxford's chemistry department. When I began studying the history of science, I learned that existing accounts of organic synthesis are dominated by theory as enabler. Even accounts of labs and experiments ultimately fall back on theory as the explanation for advances in 19th century chemistry, a formative period that saw organic synthesis become one of the world's most powerful and productive sciences. And as these quotations show, this emphasis on theory's productive power spans the literature from introductory texts to specialist studies. That didn't make sense to me, and the more I studied, the worse it got. To me, theory didn't explain anything. Not the labor required to make synthesis work, not the problems chemists faced when trying to decide what the substances they studied were, not the alteration in 19th century chemistry's scale, methods, and instruments, and certainly not how chemists learned to make desired target substances, including complex natural products. I set out to investigate. That process led me to write Molecular World, an account of 19th century chemistry that doesn't rely on theory to explain what chemists could do. Studying what chemists did, as recorded in their lab notebooks, correspondence, and publications, and how they did it, including the material culture of glassware and laboratories that made synthesis possible, led me to a fresh explanation of chemistry's 19th century development. Molecular World replaces a prior historiography of theory, atoms, valence, structure, and stereochemistry with a series of new landmarks. The glassware revolution, chemistry's move into lamp-worked glassware during the 1830s. The 1840s turn to synthesis, a response to analytical deadlock synthesis initially functioned as an additional and powerful way of investigating organic compounds, not a way of making desired molecular targets. The chemical identity crisis, the implications of synthesis for laboratory design and infrastructure, and the transition to target synthesis. This historiography transforms our view of 19th century chemistry. That's why molecular worlds are disciplinary history. The book opens with a new account of the early career of one of the 19th century's most studied chemists, Justus Liebig. This account introduces two major revisions. First, it shows how the problem of organic analysis prompted Liebig to work with small self-made glassware. Following his move from Paris to Gießen, Liebig lacked resources and had no access to Parisian instrument makers. Moving into glass was vital to his analytical project and the development of his research group, and it's how he made his famous Kalia product. This way of working so transformed chemistry that I've called it the glassware revolution. Second, it shows how that by about 1840, Liebig's analytical program was in deadlock. Contrary to received accounts, Liebig didn't solve the problem of organic analysis. Rather, he showed the limitations of analysis. Analysis still couldn't produce agreed-on formulae for organic molecules, nor could molecular formulae account for the nature of organic compounds. This is a crucial point. It's precisely because he saw that analysis couldn't answer questions of composition and constitution that Liebig set his star pupil, August Wilhelm Hofmann, who's here in the middle, to pioneer synthesis as a way of investigating organic substances. Previous histories assume organic synthesis was always a way of making things. Molecular world shows instead that synthesis began as a new investigative approach. This shift from outcome to process was powerful, setting the stage for my turn to synthesis. Understanding practice as chemistry's key driver led me to introduce the term laboratory reasoning to describe how chemists reasoned from experimental outcomes to new concepts. Theories present in this narrative, but the theories chemists relied on were the stable, established theories of their day, not the speculative theories that previous histories claim drove practical advances. That's a point I'll return to throughout this talk as the basis of a new interpretation of the nature and role of 19th century chemical theory. Molecular worlds are scholarly history, but it's written for chemists as well as historians, philosophers, and science studies scholars. Its message that practice, not theory, produced the modern discipline of chemistry matters because this moves the site of knowledge making from the individual mind to the head and hands of many individuals, revealing collaborations between chemists, students, technicians, and extended communities. Success in chemistry becomes less a matter of genius and more about training and mentorship, displacing stories of great discovery moments to reveal how chemists struggled to make sense of the world around them. That helps us understand how they built the science, highlighting strategies that remain relevant today. Learning how chemistry enrolled new people, whether these were glassblowers, people who hadn't learned Latin at school, women, Jews, or people identified as other in any way, shows that people of all kinds can contribute to science. Showing why material resources, including lab facilities and instrumentation, matter to the science, supports disciplinary advocacy at all levels of government, industry, and institution. History like this seems to me to be simultaneously much more inclusive and far more useful for students and researchers trying to make their way in the field. It's the kind of history I've been sharing with students in the sciences for more than a decade, and I'm so pleased to share it with you today. Diversity, equality, and inclusion are vital to this story. My chemists' struggles were geographically situated, and they drew on specific human and material resources to tackle them. Producing agreed facts required chemists to distribute local knowledge throughout the disciplinary community, something they did with the help of glassblowers and lab architects, as well as through their teaching textbooks and manuals. Understanding how chemists built disciplinary consensus to produce a molecular three-dimensional world forces us to rethink the meaning of standards, laboratories, and chemical theory. And crucially, it does so in ways that make chemistry more accessible, highlighting continuities between then and now, expanding our view of what it means to be a scientist, and helping level the path to research. How can history inspire students if it teaches chemistry is done by genius? The remainder of my talk uses some key episodes to illustrate how Molecular World's new historiography changes the relationship between experiment and theory in chemical practice. I'll begin by examining the consequences of the turn to synthesis, Hofmann's pioneering response to deadlock in Liebig's analytical program. Early synthesis produced many new substances that chemists struggled to identify. So my second section shows why glass was crucial in solving this chemical identity crisis. And finally, I'll outline what it took for chemists to produce nature-identical molecules in the lab, what we'd call target or natural product synthesis, about 40 years later. Throughout, I'll highlight the reasoning processes that connected lab work to theory development, forming the crucial bridge between experiment and theory that I've called lab reasoning. History is concerned with change and continuity. My talk so far has focused on continuities between past and present, and I want to highlight the making of three kinds of continuity. First, one of place. How can new compounds made in one lab, say in Berlin, be recognized and reproduced in others, say in Paris or Cambridge? Second, one of universality. How do chemical properties carefully standardized by chemists and glassware break free to become the stuff of nature, true everywhere and always? And third, what kinds of skills and material resources are common to chemistry now and in the 19th century? But I'm going to begin with a change. Hofmann's turn to synthesis was a major discontinuity in 19th century organic chemistry. As we'll see, early synthesis produced many new substances that were very similar to one another. Also produced one of the most significant developments in mid-century chemical theory, the ammonia type, taking us to the core of the relationship between experiment and theory that Molecular World refigures. This slide shows one of the tables Hofmann used to summarize results produced in his lab. He called them synoptical tables. What we're seeing here is the relationship between the collective work of a laboratory and the reasoning of its director. Hofmann expected that subjecting a series of similar starting materials to the same known reaction would produce compounds that were similarly related. Synthesis corroborated molecular formula, but it also gave chemists access to new information about how molecules were put together. Historians often highlight early synthesis as being very hit and miss, but you can see here that it's highly systematic. It was also very hard. Two reasons. The first was practical. Early synthetic products were very hard to tell apart. They often looked the same, near colourless oils or white solids, and they frequently smelled and tasted alike. Tests routinely used by 19th century chemists to identify the substances they worked with. That's the origin of my chemical identity crisis. The second difficulty was that theories of chemical constitution were hotly contested in this period. In fact, chemists didn't agree on the correct molecular formula for many substances until the late 19th century. And if you don't agree on how much of which element's present, you're unlikely to agree on how those elements are organized within the molecule, which made it extremely difficult for chemists to build shared understanding of organic compounds. As they wrestled with this problem, chemists developed two speculative theories of chemical constitution. The more established was called dualistic theory, and the newer competitor was type theory. I shan't tell you much about those theories today. You can read about that in Molecular World. What's important is how chemists interacted with them. Some were driven by theoretical allegiance, doing experiments to test or confirm their preferred theory. But Hofmann's approach was both different in character and uniquely successful in steering chemistry beyond such partisan division. As I'll show, the experimental stability in Hofmann's synthetic approach allowed him to remain theoretically impartial, adjusting his interpretation in response to accumulating evidence. So what was the ammonia type? Published in 1850, Hofmann's ammonia type provided a taxonomy of organic compounds containing nitrogen. It summarized a vast body of synthetic evidence produced by students and assistants in his lab, and it expressed the relationships between many substances in terms of which elements the molecule contained and how Hofmann inferred those elements were grouped. If you look at these formulae, you'll see how brackets are used to group the atoms and how the groupings are reflected in the names. The ammonia type was a key step in how chemists understood organic molecules, and it proved remarkably durable. Chemists today still learn this classification of amines as primary, amidogen, secondary, imidogen, and tertiary nitrile bases. Now, I've introduced the ammonia type as a durable universal theory. Next, I want to focus on a particular step in Hofmann's reasoning during this work that takes us about as local as we can go. At first, Hofmann interpreted his results in terms of dualistic theory, not because he was convinced this theory was correct, but because it was the more established theory. He made many synoptical tables like the one I showed you a moment ago, and for a long time, it all went well. It seemed that dualistic theory could explain the behavior of the compounds that Hofmann made. Then he encountered a series of experiments that didn't go as expected, a key interpretative step in his reasoning. This gap over here shows the compound Hofmann expected to make by dehydrating oxanilide here, but couldn't. And here's the key point. This finding didn't cause Hofmann to doubt any of his experiments. They were his fixed points. Rather, this was the first unequivocal evidence that dualistic theory couldn't fully account for the chemistry of organic nitrogen, which led Hofmann to reinterpret his results in terms of type theory. And again, the details aren't important right now, that is all in the book, but if you identify the element of water, which I've put in green here, in oxanilide expressed in dualistic theory and in type theory, these are Hofmann's formulations from the primary sources. And by the way, you bear in mind that water is HO, not H2O for Hofmann. You will see that in the dualistic formulation, you could remove two equivalents of water, but that this is not possible in type theory. Okay, so this crucial reinterpretation didn't shake the experimental foundations of Hofmann's work, nor did it prompt him to abandon dualistic theory in favor of type theory. That's something that you will find in the secondary literature, not in my book. Instead, Hofmann concluded both theories could be helpful in explaining organic nitrogen. Type theory worked better here, but he knew other results that were much better explained using dualistic theory. And this pluralism itself was a major conceptual advance. In other words, Hofmann gave primacy to experiment, avoiding any unnecessary theoretical commitment and adopting a pluralistic, inclusive view of theory. That's what I mean by lab reasoning. And so here I shift from the making of new knowledge at a single site to the establishing of knowledge as a universal of the discipline at all sites. And here's the question: how do chemists know what they've made? Molecular formulae couldn't help, partly because formulae remained unstable in the mid-19th century, but also because chemists knew by this time that more than one substance could have the same molecular formula, the phenomenon they called isomerism. So formula wasn't the answer, nor was theory, regardless of any prediction it might make. No theory could say what a reaction actually made. I mentioned earlier that chemists relied on appearance, smell, and taste to identify substances. Increasingly, they enlisted the help of physiologists who studied a substance's toxicity in rabbits or frogs. But these methods couldn't differentiate among the many similar substances that synthesis produced, nor could they determine whether a substance made in the lab was the same as something similar isolated from nature, an important prerequisite for natural product synthesis. What could chemists do? Well, they turned to melting and boiling points, measured using glass apparatus, hoping these numerical physical properties would help solve the problem. The decision to tackle this problem in glass was overdetermined. Towards the start of this talk, I told you about my glassware revolution, when chemists, including Liebig, turned to small, self-made glassware. By the mid-19th century, chemistry had become increasingly reliant on glass apparatus produced from glass tubing by lamp working or scientific glassblowing, illustrated on this slide with a sequence of Kali-apparat-like devices whose growing complexity enabled increasing numerical precision in chemical analysis. So why melting and boiling points? Well, around 1840, a theoretical chemist called Hermann Koppe set out to show that molecular formula determined numerical physical properties, including boiling point. Koppe's former teacher, Justus Liebig, saw great potential in this work. Liebig believed boiling points would be useful in identifying organic compounds and in assessing their purity. So when Liebig set his student Hofmann to pioneer synthesis as a new method of investigating organic compounds, Hofmann routinely measured the boiling point of all his synthetic products and shared this data with Koppe. There's a wonderful mutual interest at work there. Koppe needed reliable data to investigate the laws he believed linked composition and boiling point, and Hofmann was looking for ways of characterizing synthetic products so that he would recognize them if he made them again. Two chemists whose distinct goals led them to attempt the same thing: reliable boiling point measurements. Here's the problem. Because different chemists measured boiling points in different ways, the values they recorded weren't comparable. As Koppe lamented, what's to be regarded as the boiling point when readings for the same substance made by two equally good observers aren't in agreement? Well, Koppe tackled this problem in glass. On the right is the apparatus that he built. Using data produced in Hofmann's laboratory, Koppe learned that pure substances boiled at sharply defined temperatures. Chemists believed previously that substances were pure when they looked right, tasted right, and poisoned frogs right. But Koppe established a sharp boiling point as a necessary condition for purity. But for boiling point to be characteristic, chemists everywhere had to measure the same value, which relied on bringing together substance, apparatus, and technique, in other words, on standardization. We think of standards as intrinsic to the devices we use and regulated by national and international authorities, but those bodies were the outcome of exactly the kind of work I'm talking about. To use just one example, 19th century chemists learned that one of the best ways of measuring comparable melting and boiling points was to use the same thermometer, or next best thing, thermometers made by the same maker. This man, Heinrich Geissler, was a leading scientific glassblower in mid-19th century Germany. maker of thermometers of legendary precision and accuracy. But what made a good thermometer? And why did some makers produce so much better instruments than others? Producing and distributing reliable temperature scales was a complex process that relied on expensive equipment and high levels of mathematical and artisanal skill, far beyond any individual. This problem was recognized by another of Liebig's former students, Victor Regnault, who built a normal thermometer shown on the left, which became the most reliable standard device. All other thermometers were calibrated against this apparatus. This wasn't something you could move, it wasn't something most labs could afford, and it certainly wasn't suitable for use in chemistry. Chemists worked with mercury glass thermometers like the ones on the right. Making mercury glass thermometers that could be reliably calibrated against Regnault's device was a highly skilled activity that required chemists to employ expert glass blowers. Some of these, like Geissler, are so famous you've probably heard of them, though possibly for later work in physics rather than the groundbreaking work in making chemical apparatus that established his reputation. But most remain obscure, including Geissler's successor, Franz Müller, who made this set of chemists' normal thermometers to measure temperatures ranging from -10 to plus 360 degrees Celsius. So each thermometer covers a part of that range, allowing the chemists to pick the right one for any job. And each of these thermometers is now as reliable as Regnault's fiduciary device. We saw how Cott built a boiling point apparatus using glassware components. As chemists switched to melting points, they called on professional glassblowers to make dedicated standard apparatus. Here on the left is a melting point apparatus made for the Bonn chemists Richard Anschutz and Robert Schulze by Geissler. So the sample here sat in this inner tube, surrounded by the concentrated sulfuric acid bath, and that's how chemists achieved those temperatures above 200 Celsius, which many organic crystalline solids required. I want to focus on just one aspect of Geissler's design, concerned with the technical difficulty of measuring high temperatures. If the thermometer threads cooler than the bulb, this affected the reading so that it required a mathematical correction, which was tricky and time-consuming. Geissler's design reduced this problem by insulating the thermometer within this extended glass sleeve containing sulfuric acid vapor. But even this device didn't always ensure that chemists measured comparable melting point, which is why Geissler's successor Müller worked with the Kiel chemist C.F. Roth to produce the device on the right with an even longer neck. Melting points measured in Roth's apparatus were comparable in Kiel or Oxford or New York without correction. This made my continuity of geography, providing a stable base inside laboratories on which reliable theories could be built. In 1886, Roth used this apparatus to prove that a synthetic product made by his boss, Albert Ladenburg, was identical to the alkaloid coneine made isolated from natural hemlock. Ladenburg's published synthesis reported the melting point of coneine hydrochloride measured in Roth's apparatus as 217.5 degrees Celsius, whether it originated from hemlock or was produced by laboratory synthesis. From chemistry's perspective, synthetic coneine was identical to the natural product, a consensus that relied on the geographical dispersion of established disciplinary standards. Ladenburg's synthesis also made coneine into dextrorotatory alpha-propyl piperidine, assigning it a structure whose meaning was fixed for any chemist in any laboratory that used standard apparatus and procedures. This work generated a cascade of numerical definitions of purity and identity so robust and widely reproducible but they seemed to float free from the methods that made them. In 1873, when Frank Wigglesworth Clark tabulated thousands of melting points, he referred to them not as shared standards, but simply as constants of nature, asserting their validity everywhere and always. That's my second continuity. Chemists' efforts to understand and manipulate organic nature prompted the discipline's move into glass. This glassware revolution transformed how chemists worked, driving advances across the sciences. As they learned to work in glass, chemists called on the skills of glassblowers to build standard apparatus that mediated their ability to control and manipulate the molecular world. And that's my third continuity. Chemistry today still relies on scientific glassblowers who give material form to chemists' experimental visions. But this continuity of skill, material, and resources is frequently invisible in scientific publications that rarely name, let alone credit, the technicians who made the work possible. And in the final section of my talk, I'll use the example of Conine to show why working in glass was essential to natural product synthesis and how this destabilized the distinction between artificial and natural substances, producing new definitions of identity that linked characteristic values with three-dimensional molecular structure. Ladenburg's 1886 Conine synthesis was a key moment in the history of chemistry, encompassing three major claims. First, Ladenburg used melting points to demonstrate the identity of his synthetic product with natural conine. Second, his claim to the first total synthesis of a vegetable alkaloid was swiftly acknowledged by his peers, indicating community agreement. And third, making conine allowed Ladenburg to assign its molecular structure. And it was at this point that Ladenburg began to accept a theory he had hitherto rejected, the theory of aromatic structure. And just note that date, 1886. That's what I mean when I say that synthesis drove theory. And it's what I mean when I say that lab reasoning linked wet chemistry to abstract structure. Let me give you just a flavour of Ladenburg's accomplishment. While trying to make conine, Ladenburg learned his chosen starting material, commercial picoline, was far from pure. So with the help of his assistants, including Roth, he devised this glass distillation flask to purify it. After much trial and error, and using an additional process that separated substances according to their crystal forms, Ladenburg and Roth showed that commercial picoline was not one substance, but three. And they used synthesis to link those substances to distinct structures. Synthesis produced new definitions of substance based on specific methods. This work reinforces the collaboration underpinning achievements that the published record tends to associate with individuals, highlighting the importance of material resources and technical skills in making new knowledge. Ladenburg's decision to illustrate crystal morphology alongside his distillation flask reflects the integration of glassware and macroscopic manipulation with theory in his chemistry, and it provided essential information for anyone wanting to repeat his work. This connection between experiment and theory enabled Ladenburg to link crystals of defined shape and melting point to molecules with a specific formula and three-dimensional structure, changing a substance's very identity. That's laboratory reasoning. This rootedness of chemical knowledge in laboratory practice was essential in lab reasoning's ability to drive further experimentation. Only after finding conine's molecular structure did Ladenburg seek to rationalize these findings in the framework provided by Van 't Hoff and Lebel's still controversial 1874 theory of atoms in space, or stereochemistry. Ladenburg soon identified this carbon as a so-called asymmetric carbon by the four different groups attached to it. This made sense of the observation that alpha-propylpiperidine existed in two isomeric forms. And Ladenburg used this explanatory success to propose a three-dimensional structure for coniine, which then led him to predict the existence of similar substances that were as yet unknown. These predictions offered a way of testing the Van 't Hoff-Lebel theory. If the predicted substances could be made and behaved as theory suggested they should, this would be valuable evidence in favour of the theory of atoms in space. But there are two important caveats in how we interpret this chain of lab reasoning. First, it was hard for chemists to shift from the taxonomic and linear reasoning that had characterized chemistry for much of the 19th century to the visual and spatial reasoning associated with three-dimensional structures. Ladenburg's interpretation of the 3D structure here led him to make predictions that someone more familiar with the theory would recognize as flawed. It was far from obvious to Ladenburg how to read this visual representation of atoms in space. Second, stereochemical theory didn't tell Ladenburg or anyone else how to make the molecules it predicted. Instead, this synthetic work built on collective laboratory knowledge of reactions, techniques, apparatus, and substances. In other words, theory summarizes and suggests new possibilities, but it can't say how these might be achieved. Just as Ladenburg's synthesis of coniine established rather than being enabled by its structure, so it would be the preparation of new substances that would confirm, refute, or modify stereochemical theory, and not the other way around. Establishing the primacy of practice in synthetic organic chemistry in no way excludes theory, but it does require that we revise our view of what theory meant to chemists. As Ladenburg put it, chemists' theories might be regarded as the temporary expression of a certain series of facts, which are thereby explained in the most practical way for us. That's why lab reasoning was chemists' vital bridge between experiment and conceptual advance, a continuity that spanned the shift from two-dimensional to three-dimensional molecules, and from linear taxonomic classification to visual and spatial reasoning. 19th century chemical theory remained tethered to its experimental basis, requiring a shared foundation of technique and instrumentation for its apparent universality. That's why melting and boiling points, measured in standard glassware, displaced dead frogs as ways of characterizing and identifying substances. Ensuring that all chemists, wherever they worked, could produce the same results and interpret them the same way meant standardizing apparatus and methods, something that was only possible within the confines of the labs 19th century chemists built to enable their reasoning processes. Collaborations between chemists and glassblowers reshaped the laboratory as a productive environment for working in glass. That's why synthesis drove changes in the laboratory landscape that were essential to chemistry's control over the micro world and its ability to theorize the molecular. In other words, chemical theories were unlike their mathematical counterparts in physics, a finding that both reinforces the desirability of positioning chemistry at the heart of any philosophical account of the sciences and illustrates the contribution that the history of chemistry might make to that endeavour. I want to conclude by reflecting this history back onto the relationship between history and chemistry. This talk's offered an account of chemistry that emphasises its collaborative nature and material basis. It's highlighted the essential contributions of people not usually called scientists, and of the students and assistants whose work is often attributed to their mentors. It's illustrated the range of skills and resources involved, not just in making science happen, but making it work reliably beyond its original location. And it reveals lab reasoning as a durable approach to navigating the relationship between experiment and theory in chemical practice, and thus a vital component of research in chemistry. These historical revisions remain crucially relevant in the present. They're the foundation of the new teaching-led research project that I'm developing with chemists in Oxford. And I'll tell you just a little bit about that, which I hope will be of interest to this audience. As a first step, we introduced 2 lectures for the 4th year cohort in the MChem degree, and this coming year we are planning to make those lectures open to students at all stages in their chemistry degree, translating history into innovative best practice in chemical training and research, supports new chemists and inspires experienced practitioners. And the second part of this development is a new 3rd year option called Understanding the Chemocene. And this option provides a history of modern chemistry that reflects molecular world's practice-based orientation, offering fresh perspectives on chemistry's place in the world. Chemistry, like other sciences, is facing unprecedented challenges, but history is replete with creative strategies used by chemistry's greatest innovators. Histories like the one I've outlined today help foster the diversity that's vital to disciplinary sustainability. And that's why I'm committed to engaging scientists seeking to understand, perhaps even to join, their struggle with global problems. History and chemistry are so much stronger together. Thank you very much.
Thank you very much indeed, Catherine, for that fascinating talk. In particular, I particularly like the idea that your course, as well as making for better chemists and better research, might encourage more working chemists to take up the history of chemistry, even if they don't become professional historians.
Hurrah.
Certainly to be welcome.
Mm.
My first comment, I haven't had any questions so far, but I will ask, I'll say a couple of things myself, and then maybe somebody will be encouraged to pile in. The first thing is, it's not so much a question as an observation, but if chemists could not be sure of what the compound was based on its formula or even its structure, given that the structure was often unreliable in that period anyway, it shows to me, and I've never thought about this before, but it shows to me the importance of naming, because if you name something, you know what it is. I mean, okay, you might not be aware of some aspect of it, but if you've made something new and it has the same formula as something else, at least you can say, this is it because I call it this. And therefore that, to me, gives a heightened importance for nomenclature, which is often overlooked, because normally when we consider chemical nomenclature, we say something like, oh, look at those weird names they came up with, and how on earth did they think they made any sense? And wasn't it a jolly good job that they came along and produced a systematic nomenclature? I mean, I'm thinking, for example, of Evan Hepper Smith's work on the Geneva nomenclature. Your work, seems to me, put a renewed emphasis and importance on trivial names. But even if the names themselves are, in this deprecatory sense, trivial, at least it gives that particular substance a point of identity. But
or does it? Or does it, Peter? I mean, there's an example in the book, the example of camphor, which as a substance caused huge problems because what chemists called camphor in fact wasn't always the same thing. So you're quite right that if one person makes a substance in the laboratory, they can say, I have made this substance and this is what it is. And it's possible that they may be able to repeat that experiment to produce the same substance, although that is by no means guaranteed, because as we know, very minor variations in procedure will, in many situations, produce at least a slightly different substance. So that is an example of what one might call highly localized or even individual knowledge. And one of the things that I think is really significant about the history of 19th century chemistry is this vast disciplinary development. And in order to build a discipline, you have to have shared knowledge. And so what one person knows. So I think you're quite right that names are highly significant. Of course, it's also worth noting that the establishment of naming conventions that are shared is a 19th century thing. If you think back to the tables for the ammonia type that I showed you, I mean, Hoffmann has a highly systematic approach to naming, which he is quite successful in establishing throughout the majority of the chemical community, although he, of course, would be the first to admit that it was somewhat, what's the word I'm looking for? It was quite unmanageable, actually, which, of course, in the end is why working chemists, certainly working organic chemists, tend to work with skeletal formulae these days. I mean, we don't use, in fact, practicing chemists don't rely all that heavily on systematic names. So yes, I mean, it's a very interesting series of comments, and of course, much that one could say, but I think some of those issues around the individual and the collective disciplinary, and some of the issues of this around kind of it's a historical phenomenon that chemists tried very hard to systematize their naming.
Yes, I mean, okay, just to come back very briefly, but identity is all very well, but what's the point of establishing identity if you can't crystallize that in some way? I mean, crystallize is maybe a good word in that context. You need some way of putting a label on it to say, I mean this compound. That's basically what I'm saying, but I entirely agree
Well,
with
I think that's basically what I'm saying, actually, Peter, because that is the point about the shift to measuring melting and boiling points, and it's, of course, intimately related to the fact that in the 19th century, if you can't crystallize it, you don't have anything. That's a very bad paraphrase of the famous remark made by Richard Billstetter later in the century, that if you can't crystallize it, you've got nothing to work with. So, yes, being able to assign melting and boiling points and using those as characteristic values, and all of this work in glass and in laboratories that allowed chemists, and by glass blowers, that allowed chemists to make melting and boiling points into characteristic values, such that they could become things called constants of nature, not characteristic values very carefully stabilized by an enormous amount of work, but things that are just natural. So that's really my story there. Yeah, agree with you.
Okay. I've got one question, which is related somewhat to my comment, and that is that I have myself sometimes made the comment in my publication that formulae and even structures, particularly structures as much as formulae, for chemists up to about 1950 were not so much a matter of telling you what the molecule looked like in reality, as much as a summary of what had been found out about that compound. It was a way of storing that chemical knowledge that you're talking about within a single thing, namely the structure. Would you agree with that?
I mean, broadly speaking, in my period, which probably doesn't go quite as far as 1950, but broadly speaking, I would say that most chemists are actually fairly agnostic about issues of reference. I mean, there are some very famous examples and some very famous, so Kekulé is a great example of somebody who is very famously, at least apparently, somewhat shifting in his attitude towards a realistic interpretation of formula and structure. And there is Alan's wonderful work on chemical and physical atoms pertaining to that. There is also the very major debate philosophically. This is something that John Brooke wrote very nicely about in relation to Gerhardt and Laurent, as to whether what one learned by doing wet chemistry had any bearing at all on actual three-dimensional structure. So certainly in the 19th century, there are these debates ongoing, but from the perspective of many chemists, as you experience them at work, when you read the sources, it's a peripheral matter, not a central concern for most of them. I think that's what I would say.
Okay, very good. I've got one question, and it relates to your project. And this is from Abigail Bellamy Carter, who says, encouraging students to look at the history of chemistry, do you think this has a role in getting them to consider the language of modern chemical communication, both public and scientific publications?
Well, I certainly hope so, and I mean, it would be interesting to know a little bit more what's driving that question, in the sense that, I mean, if that's coming from a point of view of it would be great if scientists were better at communicating their knowledge and communicating what it is they do to wider publics, then absolutely so. And I think especially in an age where, you know, there is in a wider public, there is quite a lot of, I would go even so far as to say, certainly concern with, and in some instances I would see hostility to chemistry. I mean, I think as people are more and more occupied by issues around the environment and pervasive chemicals and so on, and you know, that's not restricted to communities beyond the academy. You know, there's quite a lot that happens in the humanities academy that has something of that flavour. So I think one of the things, so you know, that there are a number of goals for this programme. One of them is quite internal to the science, if you like, in the sense that the pedagogical purpose here really is to support and enable new generations of students of all kinds to see chemistry as a, you know, a viable degree course and possible career. And I think, you know, that's a very significant thing to do. But I think there's also a set of issues around how those people, that, you know, the quite numerous people who do a first degree in chemistry and then go to work in other fields, how they can continue to be ambassadors for the field. So I think there are, you know, there is something around how you enable the transition from being somebody learning taught material, stable material, to being somebody who's being a researcher, which is, of course, in the Oxford degree structure, which is a 4-year undergraduate degree, the final year is a research year. So by tapping into 3rd years and 4th years, one of the things that we're trying to do is to support that transition to research. But there is also that more public-facing component, for sure. Yeah, I mean, making people doing chemistry degrees actually write something in prose, extended prose, is already an interesting move, because it's a long time since chemists had to write essays as part of exams.
Yes, I mean, do you find that the result of the course you give, that anybody changes what they do, either in terms of a research topic, or maybe do afterwards, or perhaps you haven't been doing it long enough to find that out?
That's a really interesting question, and obviously that, you know, to some extent that remains to be seen, Peter, because this is, you know, that you're getting this fairly hot off the pedagogical bench, but I think that, I mean, one thing I'll say is that the uptake for these things indicates there is a real appetite among the students for this, and there are preliminary signs that this is something that certainly is gives pause for thought, opens different kinds of conversations, supports a different sort of interaction, both with the academic and technical content of the degree, but also with chemistry as a field.
Yeah. Okay, well, I think that's a good point to stop, Catherine, and thank you once again for a very thought-provoking and interesting lecture.
Thank you very much for being here, and thank you, Peter, for sharing.
No, thank you. And thank you, everybody, for coming along and listening to Catherine. We do both appreciate that. Now, next month, we're having Jeff Rayner Canem again. He's going to talk to us about 12 women chemists you've probably never heard of, and you probably don't know who they are. I think I've got that the right way around. But anyway, he's talking about 12 women chemists you ought to know about, but probably don't. I think that'd come closer to his title. So please join us again next month, same time, same place, third Tuesday of the month at 2 p.m. And I look forward to seeing you then. In the meantime, I hope you enjoy the rest of the day. And once again, thank you very much, Catherine. Bye for now.